All right, and we are back with part 2 of chemical equilibrium. So let's jump in to some of the procedures we use for calculating equilibrium concentrations. So stoichiometry can be used to determine the equilibrium concentration of all of our reactants and products if, these are the big ifs, you know the initial concentrations of everything, and you have at least one equilibrium concentration. And this is really handy because in our earlier scenarios, we were using the equilibrium concentrations of everything and just solving for K. However, even though that's very direct, it's not always plausible because you have so many more experimental conditions to ascertain the equilibrium concentration of every single reactant and every single product. To do that, it's much easier to set up a reaction with known reactants and then go towards and then identify the concentration of one product or one reactant at equilibrium, and then you can do all the things we're going to do moving forward to come to K. So what we use is called an ICE table. And ICE table, we're going to go into a bunch of different scenarios with it, but that's initial, change, and equilibrium, or what IC and E stand for. And we're going to use the change in the concentration of whatever substance we know to determine the change of all the other chemicals in the reaction based on their stoichiometry, those molar ratios of molar equivalents in the reaction. So this is what a nice table looks like. And you can see on the y-axis we have initial, change, and equilibrium, and then on the x part of the grid we have our reactants and products. And this particular example is going to be for the generic reaction of reactant A is in equilibrium with reactant B, and in this particular case we have 1 molar equivalent of A produces 2 molar equivalents of B. And both of these are gases, so both of them can participate in our equilibrium calculation. So let's say we set up a reaction mixture in which the initial concentration of reactant A is 1.00 moles per liter. And under these initial conditions, because no reaction has taken place yet, the initial concentration of B is going to be 0 moles per liter. And then after reaching equilibrium, we determine experimentally that the concentration of A is now 0.75 moles per liter. Because there's a delta, or a difference, of negative 0.25 moles per liter in the concentration of A, for every mole of A that is consumed as a reactant to this reaction, 2 moles of B will be produced. This means that because we lost 0.25 moles per liter of A, we will gain 0.5 moles per liter B. And this is what we're going to plug into our table. So initially, we've got 1 mole per liter of A and 0 moles per liter B. We know experimentally that the concentration dropped to 0.75 moles per liter for A at equilibrium, which means there's a difference of 0.25 moles per liter, which we can see here in our change for A. And then because there's 2 moles of change per mole change, 2 moles per change of B per 1 mole change of A, we have 2 times 0.25, which is going to be 5. And then equilibrium is going to be our difference. So we're minus 0.25, which gives us our 0.75, and we are plus, because it's product, 0.5 plus 0 is 0.5. So now we've got equilibrium concentrations for both A and B, just using stoichiometry in this ICE table, and we can plug that into our equilibrium expression for this reaction, which in this case would be B squared over A, and that would give us a K value of 0.33. for this particular reaction. So let's do a slightly more complex example using the size table. Let's say for the reaction, carbon monoxide gas plus 2 equivalents of hydrogen gas are going to be an equilibrium reaction forming methanol gas. In this particular case, we're going to do the reaction at 780 degrees Celsius. So that's going to mean that our K value is going to be specific to that reaction temperature. And initially, what we're going to put into the reaction container is going to be 0.500 moles per liter of carbon monoxide, 1 mole per liter hydrogen gas. And then at equilibrium, we're going to find that the concentration of carbon monoxide becomes 0.15 moles per liter. So using this information, what's the value of our equilibrium constant? Okay. So let's set up a ice table here. What do we know initially? Well, our initial concentrations for this reaction is carbon monoxide is 0.500. Hydrogen gas is 1.00, and initially methanol will be 0 because it's a product and we're just adding reactants initially. And we also know the equilibrium concentration of the carbon monoxide is 0.15, so we can fill all those in. So what's the difference for the equilibrium to initial for carbon monoxide? In this particular case, it's going to be a negative 0.35. because concentration went down 0.35 moles per liter. Knowing that information, what we can then do is look at our molar equivalents in our stoichiometry, 1 to 2 to 1, and we can propagate the 0.35 across our table. So we know also that our concentration of hydrogen gas is going to go down because it's a reactant. So it's going to be minus 2 times 0.35, and our concentration of methanol is going to go up plus 1 equivalent, which is going to be plus 0.35. And we can see those on the bottom ice table. And then we can just simply do our arithmetic, where you can see that our hydrogen is going to go down, our methanol is going to go up, and we have equilibrium concentrations for both reactants and our product. Now that we have all those, we can plug them straight into our equilibrium expression. So products over reactants is going to be methanol raised to the first power over carbon monoxide to the first power times hydrogen gas squared. Plug in all of our values, and we will see that we've got a equilibrium constant of 26 for this particular scenario. So let's add another layer to this. Let's look at the reaction quotient. So if a reaction mixture containing both reactants and products is not at equilibrium, at any moment instantaneously, we can determine which direction the reaction will proceed as it reaches equilibrium. And the way we do this is we find the reaction quotient Q. So what that is just the non-equilibrium concentration ratio of products over reactants raised to their coefficients respectively. So it's exactly the same calculation we do to find K, but we do it at non-equilibrium conditions. And then we can compare Q to K and determine which direction the reaction will proceed. So for everything in gas phase, for our generic A plus B goes to C plus D scenario, just like we would calculate K, we can calculate Q, either for concentrations, where Q sub C, or using partial pressures, Q sub P. So how would we look? Well, and I'm not going to go through actually calculating Q because it's exactly like calculating K, but just at non-equilibrium conditions. How do we use Q to predict direction of change? Well, if Q is greater than K, that means the reaction is going to proceed fastest in the reverse direction. And that makes sense because think of K or Q as products over reactants. Well, if K is larger, that means we have an excess of products compared to our equilibrium condition, which means the reaction is going to proceed in the reverse direction towards our reactants. So in this scenario, our products will decrease and our reactants will increase. Conversely, if Q is less than K, the reaction needs to proceed fastest in the forward direction. This also makes sense because if you're thinking in the context of K equals products over reactants, if Q is less than K, that means there are fewer products than there should be at equilibrium, so it needs to continue towards products. So you can intuit this relationship a little bit. And of course, if you measure what you think may be Q and happens to equal K, that just means you're at equilibrium, because if Q equals K, there's no impetus for anything to change, because K, if you're at K, you're at equilibrium. So, finding equilibrium concentrations given K and initial concentrations or pressures. This is a little different because what we've done previously is we've determined K with ice tables. Now what we're going to do, conveniently, large numbers of reactions, equilibrium constants have been calculated under standard pressures and temperatures. Because of this, you can ascertain or predict equilibrium concentrations for a known reaction if you go look up the K and you have initial concentrations or pressures available to you. We can actually predict what you should get out of a reaction. So, general steps. This is a little bit, there's a few steps to this, but it's not really complex, it's just steps. So let's just kind of work through a few. So step one, you set up your ice table, initial, change, and equilibrium, like we did before. And then you decide which reaction the reaction will proceed. Now this seems like a lot of work initially, but for a lot of these reactions, everything's going to be under initial conditions, so you know under initial conditions that there are no products yet, and the reaction will proceed forward. That's not every single question that we address, but often it just becomes a mental check that you have to do versus actually calculating Q and K and doing a comparison. So that's a quick check. Step 3, define the changes of all substances in terms of X. And this is where it seems a little abstract just saying it, but because we don't have a true delta, because we don't have a final concentration to compare to our initial concentration, we're just going to have to say that our delta is X, raised to whatever coefficient is required from the stoichiometry of our balanced equation. And then we just solve for X to get our delta. Then we solve for X. We plug that into the ice table, and we can calculate every actual final concentration that we're interested in. So, of course, if a reactant is being consumed, X is going to be negative, and if it's a product, it's going to be positive because the delta between our initial and final conditions dictates that. Then we solve for X. Sometimes you have to use quadratic equation to do this. Sometimes you get away with just doing a simple squares solution. And let's go ahead and do a couple just to get comfortable, because hearing that probably didn't give you a whole lot of comfort. So let's go back to that scenario we had where we were looking at just the generalizable reaction of one equivalent of A, which is in gas state, is in equilibrium with a product 2B, two equivalents of B, which is also in gas state. So they're both gases. They're both able to participate in this equilibrium process. We don't have any solids or liquids we have to account for, or in this particular case, I suppose, not account for. So let's say that we have this reaction mixture in which A is 1.0 moles per liter, and the initial concentration of B will be 0 because we haven't allowed the reaction to proceed yet. However, now we know, because we looked this up, that the equilibrium for this is going to be 0.33, where K equals 0.33. And what we want to do is predict all of the equilibrium concentrations. So that first thing, we know that Q is 0 because instantaneously the reaction has yet to proceed. Therefore, it will go towards products to some extent. So we're comfortable with writing it in this particular direction. And we can set up the ICE table to represent this. So in this particular ICE table, for initial concentrations, A will be 1 mole per liter, B will be 0 moles per liter. Our changes, because we have 1 molar equivalent of A leading to 2 molar equivalents of B, will be minus X for A, because it's being consumed, and plus 2X for B, because it's being formed in that 1 to 2 molar ratio. And then our equilibrium concentrations can be expressed as 1 minus X and 2X. We can then take our equilibrium expression for K equals B squared over A, and we can substitute in 2X for B and 1 minus X for A, and this will give us 2X squared over 1.0 minus X. And then we can square the 2X to be 4X squared, just a little simple arithmetic, and 4X squared over 1 minus X equals 0.33 will give us our solution. And the way we get to our solution, of course, is through this being a quadratic expression, because x squared minus bx plus c equals 0. So you can just rearrange that to a quadratic expression and solve. So that's the generalizable approach. Let's go ahead and do an example. Example 1. Consider this particular reaction with nitrogen gas plus oxygen gas is in equilibrium with the product nitrogen monoxide. And it's a 1 to 2 molar ratio. The equilibrium constant for this particular reaction, K, is 0.10 at 2000 degrees Celsius. So this is not going to be happening at room temperature or biological temperatures. It's going to happen at extremely high temperatures. And note that K, of course, is specific to this particular temperature. So our initial reaction conditions at 2000 degrees Celsius, concentration of nitrogen gas is 0.2 moles per liter. Concentration of oxygen is 0.2 moles per liter. And we're interested in finding the equilibrium concentrations of the reactants and the products at the reaction temperature. So first thing we can do, set up our ICE table, and we know right out the gate our initials across the board, 0.2 for nitrogen, 0.2 for oxygen, and 0 for nitrogen monoxide. Of course, we also know that the reaction will proceed towards products because the reaction just started. So Q will equal 0 because we have no products, which means the reaction must proceed as written towards products. So we're good to go there. Reaction will proceed to the right. That dictates our negatives and our positives. And for step 3, we can then, now that we know what's negative and what's positive, plug in for X. So we don't know what the change is yet, but we know that everything will change based on molar equivalence. So if we lose X moles of N, we will also lose X moles of oxygen, but we will gain 2 moles of the product nitrogen monoxide. We can then make expressions for our equilibrium concentrations of nitrogen to be 0.2 minus X. We can make the same for oxygen, 0.2 minus X, and we can make it for nitrogen monoxide at 2X. This is convenient. Because we started with the same initial concentrations of both nitrogen and oxygen, the terms are the same, which means we can simply square them. Let's see here. How do we want to go about this? Fine. So we do want to remember the quadratic formula. X squared plus bx plus c equals 0. And to solve that, x equals minus b plus or minus the square root of b squared minus 4ac over 2a. You have to be able to do this in the exam. This is a given. However, for scenarios like this particular one, note that the equilibrium expression for K is NO squared over nitrogen's concentration times oxygen's concentration. Because the expression for both the nitrogen and the oxygen are the same, when we plug them in here, we can combine them as a square also. So we have 2x squared over 0.2 minus x squared equals our equilibrium expression of 0.1. The cool thing about this is we can pull the square out by taking the square root of both sides. So we can take the square root that we're seeing right here of 0.1, and that eliminates the square on the 2x and the 0.2 minus x. No longer have to do the quadratic under these circumstances. So experimentally, if you're doing something like this, it's awfully convenient to start with initial concentrations, which are identical for all reactants, so that you don't have to do a little bit more. It saves you some math. But in the end of the day, if you're doing this experimentally, this is a trivial amount of math compared to the time that you put in. So solving becomes fairly straightforward in this circumstance. X, in this particular case, is 0.027 moles per liter. Once we know the delta for this, we can actually substitute it in for x, solve it for 0.2 minus x becomes 0.173 moles per liter for our nitrogen, exactly the same for oxygen, 0.173 moles per liter at our equilibrium concentration. And for nitrogen, because it's up 2x from 0, it'll be 0.054 moles per liter. Now that we know this, we can plug it back into our equilibrium expression, solve for K, and voila. Notice that it isn't in perfect agreement because of a little bit of rounding we did, but K was supposed to be 0.1, and here we have 0.097, and as long as you're within 5%, you know you did it right, and these are correct. So, the next couple slides are really just talking about ways we simplify math. Sometimes. If the equilibrium constant is very, very small, the position of the equilibrium is going to favor the reactant significantly, right? And under these circumstances, we can get some simplification. Likewise, for relatively large initial concentrations of reactants, the reactant concentration's not going to change significantly when we reach equilibrium, as long as our equilibrium constant is small. Because of this, we could say that our equilibrium concentration is approximately the same as our initial concentration. And that saves us a whole lot of math because we don't have to do this entire expression. If you do this, however, it's always important to make sure that your assumption of K being small enough, your initial concentrations being high enough for this approximation to worked out for you. And because of that, if the approximate value of x is less than 5% of the initial concentration, your assumption was valid and you can get away with it. However, if it's larger than 5%, you should do all the math and not make that adjustment. Truthfully, even though this is taught at 100 level, I prefer just to do the solution unless it's a very, very, very obvious scenario where the reaction does not proceed toward product significantly because K is incredibly small, and we can absolutely make the assumption that our final concentrations are nearly identical to our initial concentrations. Other than those scenarios where it's like blatantly obvious, I prefer just to do the math and become proficient at the process and be comfortable in having the right answer. That's my recommendation. So, all that aside, let's go ahead and double back and do another example. So for N2O4 gas, decomposing to 2 equivalents of nitrogen dioxide gas, we have an equilibrium constant of 0.36 at 100 degrees Celsius. So at this temperature of 100 degrees Celsius, initially we can make a reaction, start with nitrogen dioxide at 0.1 moles per liter. And we want to find the concentration equilibrium of both the nitrogen dioxide and the N2O4. So doing this, we can just set up our balanced expression with a 1 to 2 molar ratio known, and our initials for the N2O4 will be 0 because we started with the product as written at 0.100 for our nitrogen dioxide. So next, what we're going to do is check our Q, and under these particular set of circumstances, we know Q is going to proceed towards the reactant, right? Because we have no reactant, we have only product, and we know we have a fairly reasonable amount of equilibrium because K is not that large or that small. It's hovering close-ish to 1. So we're going to have some ratio, tangible ratio of products to reactants. So that known, we know it's going to go in the reverse reaction. Because of this, under these circumstances, our negative change is going to be in our product row, and our positive change will be in our reactant row. So in this case, when we look down here at our ICE table, we can see that initials 0 and 0.1 for the dinitrogen tetroxide versus the nitrogen dioxide, respectively. And change will be plus X for the N2O4 and minus 2X for the NO2. Now that we have this, we can make our equilibrium expressions where N2O4 will simply be X, and our equilibrium expression for our product NO2 is going to be our initial 0.100 minus 2X. Once we've got that, it's time to do a little bit of math. So we're going to have to substitute in our expression for K here. And of course, it's going to be product over reactant, so it's going to be NO2 squared over N2O4. And when we put our expressions in, we have to make sure we keep our square. And then, because it's squared, you have to expand your expression, right? Because you're actually doing this, so you have to do that number. You guys remember? Okay. And this will give you your expanded expression over X. You can pull X out by multiplying both sides by X, so we'll get 0.36X equals 0.01 minus 0.4X plus 4X squared. That's where I'm at right here. And then we can set them equal to 0 by subtracting 0.36X from both sides. And this gives us our quadratic. Once we've got our quadratic equation, we solve the quadratic equation directly for X, and in this particular case, X is going to equal either 0.176 or 0.014. So then what we have to do, substitute X into the expressions for the equilibrium concentrations of the reactants and products from step 4 and calculate the concentrations. And we're going to get, when we do this, we can absolutely reject the root X equals 0.176 because it gives a negative concentration. Obviously, we don't have negative concentrations for anything because you can have a concentration of a reactant or a product that's less than 0. That's typically what happens. One of the two is going to pull up a negative, and we know what we got. So in this particular case, X is going to be 0.014. That's our delta per mole in this relationship. So now that we know what X is, we can go back and plug it in to our expression for nitrogen dioxide, which was 0.100 minus 2X. Plug that in, and we can see an equilibrium concentration of 0.072 moles per liter. And because the expression for N2O4 was just X, that's super simple as well. Now we have actual values for concentrations. We plug both of those into our equilibrium expression, solve, and we got 0.37 as our equilibrium constant. Pretty good. We've checked our equilibrium constant from the beginning. It's pretty close, and I'm happy with those predictions. Whew. I know that's a lot, and it's one of the trickier things that we do in this class. My recommendation, there's plenty of problems available in the homework set to practice it, and I recommend practicing it a lot. The more you do it, the faster you'll get real comfortable with it. But don't wait for a few days before the test to start practicing. Get in there, get some repetitions in, and do it every couple days to make sure that you're making progress and you're very comfortable and you're maintaining that comfort moving into the exam. So now that we've covered the most math-intensive part of all of this, we're going to cover the last little bit of this chapter, which involves disturbing and restoring equilibrium. Because equilibrium is dynamic, and because it's dynamic, we have the ability to perturb the system. And when we do that, we can shift the equilibrium towards products, or we can shift the equilibrium away from products. We can do all kinds of things, and we're going to go through all those variables now. The most important thing to remember, anytime you change the conditions, the concentrations of all of the chemicals have to change until we restore equilibrium. That's determined by K for that particular set of reaction conditions, particularly the temperature. So if we change one concentration in play, whether by adding something or removing something, everything has to rebalance. And that means we're going to have all new concentrations from what we had before. However, K, the equilibrium constant, will be unchanged when it returns to equilibrium, as long as the temperature hasn't changed. So this is called Le Chatelier's principle. Le Chatelier's principle gives us guidance on how to predict the effects of different changes in conditions involving equilibrium. And it states that if a system at equilibrium is disturbed, the position of equilibrium will shift to minimize that disturbance and return to K. Disturbances which we are going to address include changes of concentration of a reactant or product, changing the volume or pressure of the reaction conditions, and changing the temperature. All of these fall under the scope of Le Chatelier's principle. So, starting out, adding reactants. So if a reactant is added to a system at equilibrium, as long as it's added, the added reactant is included in the equilibrium constant expression, of course, because it's non-liquid or non-solid. Questions will include how will this affect the rate of the forward reaction, how it will affect the rate of the reverse reaction, and how will it affect K. So adding a reactant initially increases the forward rate of reaction, but has initially no change on the effect of the reverse reaction. And that means the reaction is going to proceed towards products until equilibrium is restored. So let's just kind of look at that. A plus B, B, C plus D. Let's say we add 3 times our initial quantity of A. Everything's at equilibrium, and we just pour a whole bunch of A in there. Well, because K is products over reactants collectively, what we've done is we've increased the amount of reactants. And that's going to shift K to a Q which is lower than equilibrium conditions. To correct that, we have to make more products to return to K. So we're going to push the reaction in that direction towards products until K is restored through having the appropriate ratio of products to reactants. Now what's important here is at this new equilibrium position, we're going to have more products than before. We're going to have different concentrations than we had before. However, K is going to be the same. Let's evaluate what happens if we remove a reactant. So a reactant is removed from a system at equilibrium as long as the added reactant is included in the equilibrium expression, of course, because we can't do this if it's a solid. If you're pulling liquid out, it doesn't matter. If you pull solid out, it doesn't matter. It has to be gaseous or aqueous. So how does this affect our forward reaction? How does it affect reverse? Does it affect K? So let's go back to that scenario. A of A plus B of B is in equilibrium with products C of C and D of D. So removing a reactant initially decreases the rate of forward reaction, but has no initial effect on the rate of the reverse reaction. This is all initial, right? So it's going to go faster in reverse. Generally, if we have something that pulls our reactants out of solution, for the same reason that we talked about, K being disturbed. If K is products over reactants, if we're pulling our level of reactant down, all of a sudden we have too much products. We've unsettled K. And because of that, our reaction will proceed more aggressively back towards reactants to resupply the thing that was taken away. Just kind of, sharing. It's like kindergarten. So kindergarten, but for chemists. So the reaction is going to proceed in reverse to reestablish concentrations of A so that we can return K to where it needs to be. So at this equilibrium position, we'll have less of the products than before, more of the non-removed reactants than before, and more of the removed reactant. But K is going to be the same. That's the important thing to remember. And this is actually really us. Let me go forward a slide and see if I'm... Okay, yeah, we'll get there. So I don't want to get ahead of myself. So the effective concentration changes at equilibrium, part 4. Adding a reactant will decrease the amount of the other reactant and increase the amounts of the product until a new position of equilibrium is found which has the same K. Makes sense. Removing a product will increase the amount of the other product and decrease the amount of the reactants. And you can use this to drive reactions to completion. This is really slick. So let's say we have a scenario where, let's see here. Well, there are, without getting into too much advanced chemistry here, scenarios where, let's say you have a reaction where you have some reactant A and it's in equilibrium. But I'm going to draw a double-sided arrow which indicates a strong favor towards the reactants in this case. And let's say we're really interested in isolating some product B. However, this isn't a particularly favorable reaction. A does decompose a little bit to B and C. However, as we can see, the reversible arrows really favor, it's going to have a small K. And because of that, typically this would not be favorable. But let's say we have a second reaction where C and D go overwhelmingly towards some product X, which is a gas. and gases bubble out of the system. Well, the cool thing about this is we can react, we can add some D to reaction and start pulling C away. What's really slick about this now is as C leaves, even though this isn't favored, more A then has to be consumed to replace the C. And as that happens, more B is made. And then the C gets removed. And even though this isn't favorable, we can use Le Chatelier's principle to continuously make A try to replace that C that is being removed as through secondary chemistry, and keep making more and more and more of this B that we're interested in. So this is one of the mechanisms by which we can use Le Chatelier's principle to our advantage to manipulate a reaction. Okay. Effects of concentration changes on equilibrium. I want to make sure we're not getting ahead of it here. Okay. So in this particular case, if you disturb the ratios, you need to do something to get them to return to a more normal state. So in this case, we have N2O4, one equivalent of N2O4 gas is in equilibrium, forming two equivalents of NO2 gas. So what happens if we add NO2 to this? Well, in this case, because we've added NO2, we have too much of it. We need to push back towards the reactants. What happens if we change volume of reaction? So after we establish equilibrium, let's say we take a container and we compress it. So it's all these gases that are reacting, and we suddenly compress the container once we've established equilibrium. What does this do? How does it affect the concentration of solids, liquids, solutions, and gases, say? And how is this going to affect the total pressure of our solids, liquids, and gases? And how is it going to impact K? Let's go through these. Well, decreasing the container's volume is going to increase the pressure because of Boyle's law. If the total pressure increases, the partial pressures of all the gases are going to increase as well, right? And because of this, as the total pressure increases, the position of equilibrium is going to have to shift to decrease the pressure by removing gas molecules. So, in other words, the shift is going to go towards the side which has fewer equivalents, molar equivalents of gas being formed. Makes sense. So at the new equilibrium position, the partial pressures of the gaseous reactants and products will be similar, will be such that the value of the equilibrium constant is the same. So once again, K doesn't change because we changed the pressure. However, we will see a partitioning to favor reduction in total gas molecules, which means the reaction will shift towards whatever side it has fewer molecular equivalents of gas molecules, and by doing so will not change K. Some other points to make regarding this. Decreasing the volume is going to cause the reaction to shift in the direction that has fewer gas particles. Increasing the volume is going to cause the opposite. It's going to cause the reaction to shift in the direction that has a greater number of moles of gas particles. Remember that scenario as a possible thing we could ask about. If a reaction has an equal number of moles of gas on either side, which is not that uncommon, then a change in volume produces no effect on the equilibrium whatsoever. That's a scenario you should be comfortable with. And adding an inert gas to the mixture at a fixed volume also has no effect on equilibrium because it cannot participate in the reaction. So even though it's changing the pressure, because we cannot participate in the reaction, it's not going to change our equilibrium. And this is gases only. This does not apply to aqueous systems. So if I'm not going to ask you a trick question regarding that, but if somebody were to ask you a trick question on that, know this only applies for gaseous reactions. So what's the effect of adding a gas to a gas phase reaction at equilibrium? Well, adding a gaseous reactant is going to increase the partial pressure, and that's going to cause an equilibrium shift to the right. Increasing its partial pressure is going to increase its concentration. It does not increase the partial pressure of the other gases in the mixture. Adding an inert gas to the mixture has no effect on the position of its equilibrium. Once again, it's inert. So if it's not participating in the reaction, adding some inert gas to this is not going to change anything. So here's a diagram kind of demonstrating what we've been talking about. Let's say we have a scenario here on the left where we have 1 equivalent of nitrogen gas plus 3 equivalents of hydrogen gas is in equilibrium, forming 2 equivalents of ammonia gas. So here on the reactant side, we have 4 moles of gas, and over here on the product side, we have 2 moles of gas. If we increase the pressure of this once it's reached equilibrium, equilibrium will shift towards the right to reduce the total number of moles of gas. Likewise, if we, on the scenario on the right side here, decrease the pressure by moving the piston up, equilibrium will shift over to form more moles of gas because of our relationships of our partial pressures. And this is redundant, sorry. The effect of temperature change on equilibrium position. This is a good one. So, for exothermic reactions, which inherently release energy, and endothermic reactions, which absorb energy, the scenarios are different. So you need to know, is it exothermic or is it endothermic to know what's going to happen with the Chatelier's principle. So it's really nice when we're writing reactions to include where the heat is. Is heat being produced as a product of the reaction, or is heat required as a reactant to drive a reaction? And this actually will then make it intuitive as to which way we drive the reaction. So let's look at this example where for an exothermic reaction, heat is a product. So in this particular case, let's look at 1 unit of nitrogen gas plus 3 units of hydrogen gas is in equilibrium, forming 2 units of ammonia gas, and heat as a product. So if we increase the temperature, it's like adding heat, which in terms of Le Chatelier's principle is no different than adding any other product. As we perturb the system by adding more product, we need to push the reaction towards our reactants to make everything happy via Le Chatelier's principle. So for exothermic reactions, if you add heat to the system, it's like adding product, and that's going to drive the equilibrium concentrations towards our reactants in this particular case. Likewise, if you are removing heat, let's say you put it on an ice bath to pull the heat out, that will actually facilitate driving the reaction towards products. This is why K changes with temperature, because you're actually shifting the equilibrium position of the reaction by removing heat or adding heat. So lower temperatures, you're going to be shifting it towards products. And some of these higher temperatures are going to be shifting it over towards the left for exotherms. What about endothermic reactions? Well, same logic applies. It's definitely worth walking through those. So for endothermic reactions, heat can be seen as a reactant. We need that thermal energy to act as a reactant to drive the process towards our product. And increasing the temperature is basically like adding heat to the reactant side, which will drive reactions toward products. Likewise, if we were to remove heat from that, it would pull the equilibrium back towards the reactant. So adding heat to an endothermic reaction is just going to decrease the concentrations of the reactants and increase the concentration of products. And you don't have to remember this as a rule, because if you remember where heat is as a product of an exothermic reaction or as a reactant in an endothermic reaction, the logic of adding it to one side or the other will get you to the right answer. Having said that, adding heat to an endothermic reaction will increase the value of K because of that. So that is it for Chapter 16. Probably sometime early next week, I'll have the next video up for the exam recitation and work probably a lot of the problems that we went through, examples of, and more for that recitation. So good luck studying. Make sure you do lots of problems, lots of repetitions. The more you do of these, the faster you get, the more comfortable you get, and the more successful you'll be when you're being evaluated on your ability to correctly predict outcomes for these types of problems. So until next time,